Let's keep talking about survival analysis and Kaplan-Meier survival curve estimator real quick. Introduced the notation for working with censored data last time. Now that we have the potential for censored observations, we need an indicator in our data set for each event time that tells us whether or not it was an actual event or a censored time. So all of our survival analysis data are going to contain a column for the event times and a separate column for the censoring indicator. And the usual parameterization of the censoring indicator is equal to 1 if an actual event happened and 0 if it was right censored. So then we started talking about one way of summarizing event time data, that being the survival function. S of t is 1 minus the CDF at t. The CDF at t, capital F, is equal to the probability that t is less than or equal to t. So this should really be probability that t is bigger than t, strictly. So I would mark that out, the under bar under the greater than. And then in order to motivate the Kaplan-Meier style estimate of the survival function, I wanted to tidy up what we had here. So let's consider these example data again. Just 5 individuals, and we have both event time and censoring indicator. So we're going to construct a survival curve estimate in such a way that we accommodate the fact that one of these individuals, one of these event times, was actually a censored event time. So the way that we do this is we represent each of the survival probabilities as a joint probability. And a joint probability can then be written as the product of a conditional and a marginal probability. So I wanted to revisit this and make it clearer. The survival probability at time t, this is 1 minus the CDF at t, or in other words, the probability that t is bigger than little t. And we can write that last expression as a joint probability. So we can write this as the probability that the individual survives until time t. That just means they did not die at a time up to but not including t. So t is bigger than or equal to t, and that they do not die at time t. So the probability that an individual lives longer than t is the same thing as the probability that they don't die before time t and they don't die at time t. And we said last time that a joint probability like this can be written as a product of a conditional probability times a marginal. So we can write this like probability that individual does not die at t, given that they survive up to t, times a marginal probability that they survive to time t. So that probability that they survive up to time t, what we can do, or let me erase that real quick and say probability that individual survives to time t. We can estimate that as the survival estimate at the previous observed time point. So I'll call that T minus. This is the estimated survival probability at previously observed time point. So, for example, the probability, the earliest time point in our observed data here is time 3. At time 3, subject 4, we observed an actual death at time 3. The probability that I would estimate of surviving up to time t would just be the previous survival probability estimate. So before I observe any deaths or censoring, my estimate of probability of surviving would be 1. Nobody died, nobody was observed before time 3. So the prior time, the survival probability at the previous time point, initially here at time 3, is equal to 1.0. The survival estimate at time 3 is probability that they don't die at t, given that they survived to t times 1.0. So then we just need to think about what does it make sense to use as an estimate of the probability that they do not die at time t, given that they survive to time t. A sensible way to estimate the probability of surviving time t, given that you survived up to time t, is what proportion of the people who are at risk, who are still in the study at time 3, did not die at time 3. At time 3, with these data, we have 5 individuals currently under our observation. There are 5 individuals currently at time 3, and we observed 1 death at time 3. Individual 4 was observed to die at time 3. So if I were to focus just at time t, my estimate of probability not dying at that time, given that you survived to that time, is what proportion of the individuals who were at risk at time 3 survived. My survival probability, the Kaplan-Meier survival probability estimate at time 3 is 4/5. Or 0.8. So this top line is spelling out what I was just talking about. The probability that you survive past time 3 is the probability you don't die at time 3, given that you survive up to time 3, times the probability that you survive to time 3. And we said this probability of surviving to time 3, we can estimate it as 1, because everybody, or at least nobody, was observed with an event time before time 3. Mm-hmm.
So after you get like multiple time points for this probability estimate, do you fit it with a regression model? Because if by chance just nobody in your sample die at that time point, that will give you 100% survival probability, which doesn't sound like reasonable, right?
Right. So question was, do you do some sort of regression or smoothing of the probabilities? With the Kaplan-Meier estimate, you do not. Kaplan-Meier ends up always looking like a step function. So wherever we didn't observe something, it's going to be flat. And we only have jumps or drops, steps, where there were observed times. That's just the way Kaplan-Meier works. I will show you alternatives that allow us to replace the kind of crude step function with a smooth curve. The challenge with getting at a smooth curve is that we're going to have to make some distributional assumptions. So assume that survival times have a particular distribution, then you can estimate a smooth curve. But with Kaplan-Meier, we're actually not making any assumptions. All we're doing is using proportions of events at observed times. And because of that, it's nice that it's kind of no distributional assumptions required, but it does have this end result that you have a step function. It's not that big of a deal. Usually in a real-world study, you have a fair number of events. So yes, it's a step function, but it is not usually all that restrictive because you have a lot of time points. When you have a lot of time points, step function is really not much of a limitation, arguably.
You also require large sample size, right? If you only look at like 10 people, then what would be the chance of somebody dying at a particular time point?
So there's no, the question was about sample size. Do we require a large sample size? We don't actually have to have a large sample size in order to have a valid estimate. Kaplan-Meier gives us a valid estimate of survival, but we can estimate like error bars. So it's possible to put uncertainty measures on the survival curve. In fact, when we go to R and compute one, we'll see that it gives us these error bars. And with very few observations, you're going to have wide error bars. So the estimate, it's fine, but the level of uncertainty will be higher with smaller numbers of individuals, just like any kind of inference. Good questions. Let me show or talk through two more of the Kaplan-Meier calculations. I'll show you at time 5, which is another observed death, and then we'll look at time 6 and see what Kaplan-Meier does with a censored observation. At time 5, what is the Kaplan-Meier estimate of survival probability at time 5? Using the same strategy that we used above, we can say this is a joint probability, the probability you survive up to time 5 and don't die at time 5. And then express that as a product of a conditional and a marginal. Now it is probability that you don't die at time 5, given that you survive up to time 5, times the estimated probability that you survive up to time 5. So we're building a step function like this. And we have a 3 and a 5. So at a point before, just before time 5, the estimated survival probability is this right here. It's the step function just before time 5. And another way to say that is the estimated survival probability at time 3. Our estimated probability of surviving up to time 5 is the estimated survival probability just before time 5. So here I have the conditional piece, and then the marginal piece, probability you survive up to time 5, is just the previous probability, previous survival probability, in our case S hat of 3. We computed S hat of 3 up above, it's 0.8. So then we can think about this conditional piece. What is my estimate of the probability you don't die at time 5, given that you're at risk at time 5? And here again, we would ask, what proportion of the people who are at risk at time 5 survive? At time 5, we started with 5 individuals, but at time 5, this individual is gone. No longer part of the study, not at risk, because they're already dead. So at time 5, there are 4 individuals at risk. And we observed one of them to die. So the probability that I'm going to estimate for this conditional piece is what proportion of the people at risk at time 5 continued on past time 5. That would be 3 out of 4, because 1 out of the 4 died. So the Kaplan-Meier estimate of the survival probability at time 5 is 3/4 times the previous survival probability. 3/4 times 0.8 or 0.6. Everywhere there's an observed event, an observed death, the survival probability is going to drop. There will be a step at every single place where there was a death. But what about at a censored location, like time 6? The survival curve estimate at time 6 is again probability that you do not die at time 6, given that you survived to time 6, times the survival probability at the previous time point, which is now 0.6. The time 5 probability is now 0.6. So here, what we're going to do is ask, it's a conditional times a marginal again. The conditional is probability that you do not die at time 6, given that you survived to time 6. And again, we can estimate that as a proportion. How many people were at risk at time 6, and how many actual deaths were observed at time 6. Because the one individual at time 6 was censored, we are not going to claim a death at time 6. So we are actually going to say that there were 3 people at risk at time 6, and none of them died. So notice that the survival curve estimate does not change at this censored time point. The previous survival probability was 0.6, and it continued at 0.6. But it's not the same thing. We're not going to get the same thing as if we just removed that individual at time 6. Because what happens at the next time point 8, even though we didn't count that individual at time 6 as a death, at time 8, they are treated as no longer at risk. They are no longer part of our study. So this, instead of saying there are 3 people at risk at time 8, we say there are 2. A censored individual counts against or deprecates the number of individuals at risk, but does not increment the number of deaths. This is the picture that we would get. This is the Kaplan-Meier estimator for these data. Starts out at 1, estimated probability that you survive 0 or more, or 1 or more, or 2 or more, any of those is estimated as 1. At the first death time, time 3, the survival curve drops down to that 0.8 that we computed. At the second event time, time 5, which was a death, it dropped down again to the 0.6 that we computed. At the third event time, time 6, the curve does not change. It just keeps going. Then at time 8, it changes, and it changes in such a way that it's incorporating or it's acknowledging that we lost somebody to follow-up. Not to death, but to follow-up. At the end of the study, the last individual was observed to die, so the survival curve drops down to 0. 0%, or a proportion of 0 individuals who are at risk at time 22 survived. If this last time point was censored, if it was right censored, then this survival curve estimate would not drop down to 0. It would just carry out at that final value, which happens sometimes in practice. Let me show you how to compute a Kaplan-Meier survival curve. This is the serve script.r, which is under scripts on eCampus. And these are the data from the slides. Individuals 1 through 5. The observed times are 5, 6, 8, 3, 22. And the second individual at time 6 was censored. So my censoring indicator, which we're calling delta, is 1 for everybody except for individual 2. And for that person, it's 0 to indicate censored, right censored. Okay, so to fit a Kaplan-Meier survival curve, we need the survival package. We'll use a few functions from this survival package. Let me make sure we have that package installed. I think it comes with R by default. And then to actually fit the thing, here's syntax. It's a little bit funky syntax. Let me comment on a couple of things. When we're working with survival data in R, our response variable essentially is the censored variable. So if I want to fit a model that says like response, event time, modeled in terms of, or tilde, some covariates, I have to be careful in the way that I specify that response variable. The survival package expects us to bundle our event times in a special object type called capital SURV. A serve object is just R's internal way of representing censored event times. It's just a way of putting together observed event times and corresponding censoring indicators. So this function that's highlighted, serve fit, it does a variety of things, but one thing it does is fit a Kaplan-Meier curve. So I'm saying fit a Kaplan-Meier survival function estimate, and my survival data, my event times and censoring indicators, are given by this capital serve times, comma, deltas. Saying tilde 1 means I just want a single survival curve estimate. What we'll do soon is instead of tilde 1, we'll put tilde maybe treatment variable. Suppose we have a column in our data set that's treatment, 0 for control, 1 for experimental treatment. Then this function, if we were to put that as a covariate, would fit 2 survival curves, 1 for control, 1 for treatment. And it will be of interest to test, is the survival curve for treatment the same as that for control? That's a little different from things we've done so far with inference. Yeah, the classical inference, at least initially, has to do with means. What's the mean response in the treatment group compared to the control group? And we use t-tests or Bootstrap or something to do that. But one of the common ways of summarizing survival data, again, is a survival curve. So we will be interested in fitting survival curves and asking, with a hypothesis test, are they different from each other? We talked about somewhat similar things when we were doing longitudinal data, where we said, suppose we have time and some response variable, like distance in the orthodont data, and we could fit 2 or more curves. So a time course for the control group and a time course for the treatment group. We could, for example, use the splines that we met with a linear model or a GEE model, and then might be interested in asking, instead of is there a difference in the means of the response between control and treatment, we could be asking, is there a difference in these curves? Is the time course different? So if we have multiple survival curves, we can ask similar types of questions. Suppose we have a survival curve like this, red one for one treatment group and green one for another treatment group. Can we put a p-value on? Is the survival prognosis different for the 2 treatments? By the way, before we get to a named method for doing that, you know enough already to do it yourself, I claim. Bootstrap is a very flexible technique for investigating sampling distributions. So you could bootstrap your survival data, recompute survival curves for each comparison group, and get a sampling distribution of the survival curves. And then you could compute some statistic, like maybe the sum of the squared differences between the survival curve estimates, and record that as a statistic. If you bootstrap many times and get many replicates of that statistic, you could ask, how frequently under the null hypothesis is that statistic more extreme than the one we observed, and get a p-value. So when in doubt, if you don't know the magic method that applies to your specific situation, sometimes Bootstrap can make it a simple problem. Okay, so let's do this. Let's call serve fit and look at the output and look at the plot that we get. First, let's look at the output. What do we have inside this object fit? That's all I see when I just call the name fit. What if I say summary fit? When I say summary fit, I get a breakdown time by time, time point by time point, of the actual, all the pieces to the puzzle. In order to compute the Kaplan-Meier curve, the things we need are how many people are at risk at each time point and how many events happened at each time point. That's all that's required to compute this thing. In fact, I'll show you the formula for the Kaplan-Meier curve. We put it together from first principles. Let's do the calculation for time 3, then let's do the calculation for time 5, 6, and so on. But you can write it compactly this way. It is a product. At time t, it's a product over all the time points up to and including time t of how many people died, or how many people survived, divided by how many people were at risk. So this is a compact version that reproduces all these calculations that we made. And we can use that to manually confirm the Kaplan-Meier estimates. If I order the unique event times, that gave me the indices that order event times. So now if I say, give me time square brackets that ordering, those will be the ordered from least to greatest event times. Instead of 5, 6, 8, 3, 22, it's now going to be 3, 5, 6, 8, 22. And then I ordered the deltas similarly because I need to keep everybody's time and delta together. Then number at risk at each time starts at 5, and then it drops down to 4, and then 3, and then 2, and then 1. That's the number at risk at each of those ordered time points. The number of deaths at each time point are here. There was 1 death at time 3, 1 death at time 5. There was a censored time at time 6, and then deaths at 8 and 22. Then Kaplan-Meier can be written as a cumulative product. So you accumulate from the left and you product all the pieces, number at risk minus number of deaths divided by number of at risk, all the way up to each time point. So let me just run this and verify that those numbers are the same that were calculated by SERV-FIT. So the SERV-FIT output shows us every place where there was an actual event, because that's the only place where there's going to be a change in the survival curve. There's a jump at time 3 because of a death. There's a jump at time 5 because of a death. Time 6 is not even shown in the output because the survival curve did not change there. We have 0.8 at time 3, 0.6 at time 5. This 0.6 is the same as the previous one. This is at time 6. So it doesn't even have to be shown because it's the same as the previous one. That's why R doesn't show it. 0.3 at time 8, and then it drops all the way down to 0 at the final time point where we saw the final death. The summary of the SERV-FIT object shows us number at risk, number of events, and the associated survival probability estimates. And it shows us confidence intervals at each time point. So at time point 3, the estimated survival probability was 0.8, but we had a confidence interval that went from basically 0.5 up to the upper limit of a probability, 1. 95% confidence interval from 0.5 up to 1. And it does show the confidence bounds in the picture. If you say plot the output of SERV-FIT, it will show you with the solid step function, the Kaplan-Meier estimator, and then the dashed line segments are the bounds of the confidence intervals at each time point. So here is an example of, that's a lot of uncertainty. We have a valid estimate, the survival curve estimate is valid, but that's a lot of uncertainty. The estimate at time 3 is 0.8, but my confidence interval goes all the way down to 0.5 and all the way up to 1. So confidence bounds are important. Otherwise, you really have no way of knowing how much to trust the results. If we had more observations, if we had a bigger sample size, you could bet on those confidence intervals getting narrower, getting more precise in our estimate of the curve. Here's an example of that. I'm going to simulate some data that are censored. Let's create a sample size of 100. I'm going to simulate survival times. Let's say that the average survival time is 5. Population mean survival time is equal to 5. Population standard deviation of survival times is 1.5. And I'm going to allow for 30% of my observations to be censored. So pi1 is just a parameter that I'm putting in here so that I can specify how much censoring do I want to allow for. Pi1 is proportion of people who are not censored, so I'm specifying 30% censoring. Then I can simulate the actual survival times. So I'm just simulating from the normal distribution. Capital Y now is the complete data. If we observe death for every single individual in our data set, we would have capital Y. But in practice, we often have censoring, so I'm going to randomly pick 30% of my 100 people, and for each one of them, I'm going to subtract off a little bit from their death time. I'm going to randomly generate some positive numbers to subtract off of the actual death times. And for each of those individuals, we're going to write down delta equals 0, right censored. So here are the data. Event times, censoring indicators. I have a box plot of those who were censored next to those who were not censored. So all of these individuals had the same mean survival time of 5. So the distribution of the uncensored individuals looks like the population. Has a mean of 5, standard deviation of about 1.5. The distribution of the censored individuals is biased downwards or shifted downwards, because whereas the true event times were centered at 5, every one of these individuals was observed last sometime before their actual death time. I'll skip that plot. Let's look at what the survival curve estimate looks like for these data. Let's just plot it. 30% censoring with 100 individuals, so much less, the step function element is less restrictive here because we have so many event times. It's more nearly a continuous function. And notice that the confidence bounds are much tighter. So the bigger the sample size, the more precise this estimate is. What if we change the amount of censoring? Let me set ourselves up to make a few pictures. MF row. I'm going to make 4 or up to 4 pictures. The first one will be the one we just made. This is n equal 100 with 30% censoring. In fact, let's put a title on this. Main equals n equal 100, 30% censored. Now let me remake that before I go forward. Now let's see what happens if we were to change from 30% censoring to, say, 50% censoring. I don't want to make those plots, though. I'll come back. So now we have 50% censoring. What do we see? See kind of hard to see. But what we should have is that the survival curve estimate, the confidence bounds, I would expect to be a little bit wider, but it's hard to tell if they are. In the lower or in the upper end of the time, it does look like the confidence bounds here are a little bit wider than they are here.
Well, they are not supposed to be wider at all time points.
Not at all time points.
What?
Not at all time points, yes.
Yeah. So you would expect those sensor data to affect only at longer time points, right? Because if they drop out like at the mid time, at the third time point or the fourth time point, they should affect your confidence at first or second time point, right?
That's correct. So wouldn't expect impacts on the lower end because most of the censoring is affecting the upper end. It looks to me, I can't tell by looking at it, I would expect there to be the survival curve a little higher on the upper end of the time points because more of these individuals were observed deaths, which are pushing down the survival curve. And more of these were censored, which are enabling the survival curve to continue at its previous point. So I do think from looking at this, it's hard to tell, but I think that the right picture has higher survival probabilities than the left picture, in this region at least. What happens if we change the sample size? Let's try just 20 with 70 or 30% censoring. And then let's try 20 with 50% censoring. Okay. Yeah, I think the N, I think I did. So the second row, first column, I think I didn't get the, I don't think I changed that one. I'm not going to run through all of those again because I had to do them one by one. But I would expect a similar pattern as we saw up here with bigger survival probabilities when there's more censoring. We can see that with a much smaller sample size, the confidence bounds are quite a bit wider. The more observations you have, as with any statistical procedure, the more precision you have. Okay, let me go back to the notes for a moment. Kaplan-Meier, widely used, been around for a long time. There are alternatives. I'll show you this next time. This is the function that you would use if you wanted to test. If we had a treatment group and a control group and we wanted to test, is the survival curve the same? There's a function called survdiff. And it does what's called the log rank test. If we have time next time, I'll show you the nitty-gritty details. So there's a blurb in this serve script that looks at an example data set where we have two comparison groups. I have event times for group 1, event times for group 2, censoring indicators for group 1, censoring indicators for group 2. And this just maps out what the exact calculations are for the Kaplan-Meier or for the log rank test. It's based on a hypergeometric calculation. So that's for later. but let me just briefly show you these slides real quick. The next couple of slides, beginning at slide 12, are working us towards a likelihood representation of censored data. So we remember hopefully what a likelihood is. If we just have, say, normally distributed data, if we have a random sample, IID data from some normal distribution, then the, quote, likelihood is the product of the densities evaluated at the observed data. It's, roughly speaking, the joint probability of seeing your observed sample. And we like likelihoods because they give us a systematic and defensible technique for doing estimation and inference. Namely, if you can write down a likelihood as a function of some unknown parameters, here I'm calling them theta, then a sensible way to estimate theta, which could be a mean, could be a couple of means, could be regression coefficients, could be anything. A sensible way to estimate those is to choose the values that correspond to the maximum likelihood. What parameter values would make it most likely for you to have seen the data you saw? Maximum likelihood is a tried and true technique for doing inference. So we're going to be interested in trying to do maximum likelihood with censored data. The challenge with censored data is I have some individuals who were observed to die at a specific time. So if I have some density, PDF, that I think applies, a likelihood would be the product of the densities evaluated at our observed times. But some of our individuals were censored. And for those individuals, the contribution to the likelihood should not be the density, rather it should be the survival probability, 1 minus the CDF. Because any individual who was right-censored, all we know about them is that they lived greater than or equal to YI. So we'll see this a few times going forward. The likelihood for right-censored data is a product of two pieces. For individuals who were observed at a specific time YI, it's a density. For individuals who were censored, it's 1 minus a CDF. And then by raising each of these pieces to either delta or 1 minus delta, we automatically turn on or off the appropriate pieces in the likelihood calculation. So individual I, if they were observed to die at YI, their delta is equal to 1, which means the contribution for that individual is this one. This over here would turn into 0, and that piece would disappear for that individual. For another individual who was right-censored, their delta would be 0, so this piece disappears. And this would be equal to 1, so this piece kicks in. I'll review this next time, but it's going to allow us to do likelihood-based inference with survival data. And then beyond that, we're going to learn about a different summary measure with survival data called the hazard. And the reason we like that is because it allows us to do regression. We're going to say hazards at time t is some function of covariates. Specifically, we'll say that log hazard is a linear function of covariates. We'll be regressing log hazard on beta 0 plus beta 1x plus beta 2z and so on. We have to do a little bit of jumping through hoops before we can get there because of technicalities with censored data, but we'll learn about it. Okay, homework, next homework is coming, hopefully tomorrow. And yeah, okay, I'll see you Friday.